Hello, my name is Reza Khalili and I'm here to talk to you about seismic behavior factor of single layer parallels. Nowadays, space structure are used widely in construction, especially for curving large areas such as gymnasiums, stadiums, aircraft hangars, railway station, and so on. Here you can see some important type of space structures like dome, barrel vaults, tensegrity, freeform, and foldable structures. But the important question is, what makes space structures special? I can mention two important factors. The first one is lightweight. The elements used in this type of structures, pipes and boxes, are much more lighter than other material like concrete and steel. Also, cladding can be ETFE, polycarbonate, or glass. And another factor is high in redundancy. This characteristic make structure more resistant to earthquake. In this research, we concentrate on single layer barrel vaults. Two features of these structures are shape, which is made of curved lattice along one direction, and abutments, in supports are used along the length. The seismic parameters that used in this research as follows. Behavior factor is equal to R mu times Rs. R mu is ductility reduction factor, and we use Newmark method for computing this parameter. And the another one, Rs0 is overstrength factor. We compute Rs0 equal to Vy divided by Vs and then multiply this value by 1.155. This value consider the effects of difference between the nominal and real stress of material, the effect of non-structural element, and etc. In finite element point of view, it is used elastoplastic model in order to consider nonlinear behavior of material, and analysis have been done by Abacus finite element software. In this research, 9 models are designed and analyzed with 3 rise-to-span ratios, 0.1, 0.3, and 0.5, and also 3 different lengths, 20, 40, and 60 meter. Span is fixed by the length of 20 meter. For pushover analysis, at first we need to define target displacement. But how? We follow 3 steps as follows. Step 1. Such are analyzed using time series analysis according to 20 earthquake records. For each analysis, a displacement at each control point is obtained. After completing the analysis, the average of the 20 obtained displacement is considered as the target displacement in a pushover analysis. For earthquake record, we use the assumption that soil should be type B and C, and far-field ground motion also is assumed. 20 earthquake records have been selected for time history analysis on the horizontal component. Furthermore, the magnitude is restricted between 6 to 7.5. As an example, you see pushover curve for model with rise-to-span ratio of 0.5 and lengths of 20, 40, and 60 respectively from left to right. The displacement were monitored at control point, and finally the results of analysis are according to this table. For more clarification, I would like to explain factors as a graphical representation. This curve shows the comparison of the obtained values of the force reduction factor for different lengths and rise-to-span ratios. According to this curve, due to lack of yield in the structure with a rise-to-span ratio 0.1, the value of force reduction factor is equal to unit in this span. In fact, in structure with time period greater than 1 second, the force reduction factor is equal to the ductility factor. The maximum force reduction factor is related to the model with rise-to-span ratio 0.5 and the length of 20 meters, which is 1.44. Generally, the difference in this factor for rise-to-span ratio 0.3 and 0.5 and the different lengths is negligible. This curve shows the comparison of the obtained values for the overstrength factor for different lengths and rise to span ratio. Against like previous curve, due to lack of yield for the case with rise to span ratio 0.1, the value of overstrength factor is equal to 1. In the evaluation of overstrength factor, in order to consider factors such as difference between the yield stress and the actual material stress, the effect of non-structural elements and so on, the obtained overstrength factor is multiplied by 1.155. That's why the values for the rise to span ratio of 0.1 equal to 1.155. By increasing the length of barrel walls in rise to span ratio of 0.3 and 0.5, the overstrength factor has increased. In addition, increase in the rise to span ratio leads to increase the overstrength factor. The rate of change in the rise to span ratio of 0.5 has increased with an almost constant ratio, while in the rise to span ratio of 0.3 and the length of 60 meters, the difference is more significant. The maximum changes in the overstrength factor are observed in the ratios of 0.1 and 0.5, and the minimum changes are observed in the rise to span ratio of 0.3 and 0.5. And finally, in behavior factor curves, you will see by increasing the rise to span ratio and increasing the length, the amount of behavior factor will increase. Here you see some conclusion that I explained you in previous curves. And thank you for your attention.